everyone, I'm Professor Harrison, and welcome back to our module on Calculus for Finance. Today we're going to be covering critical points and the first derivative test. These are the tools you use to find the maximum or minimum of a function. We're following Victor, a fund manager whose edge is slipping and he can't figure out why, working through a stack of letters from the manager of a competing fund called the Rational Quant. Today he's sizing a new position that the fund wants to buy. He's not exactly sure how much he should get. The problem is that he knows this purchase will give him some abnormal returns. However, the company he's trying to purchase is relatively small, so he knows that if he purchases too much, it's going to push the market price, and the cost of executing the trade will outweigh any abnormal returns that he would have made. He opens up the letter from his anonymous correspondent. Up to this point, we spent a lot of time computing derivatives. The derivative tells you the rate of change at any point. The bigger payoff is when we use it to find the points where a function reaches its highest value or its lowest value. That ends up being one of the most useful things that calculus does, and it's where we're going next. The starting observation is simple. If you're standing at the top of a smooth peak, then the slope at that peak is flat. The same is true if you're standing at the bottom of a smooth valley. The slope is going to be flat there too. So if a function reaches a maximum or minimum at some point, the derivative at that point has to be zero. That gives us the first concept of the video. We'll call these flat slope points critical points. A critical point is a point where the derivative equals zero. They are the candidate for being a maximum or a minimum because every smooth maximum and minimum has to be a critical point. Now, being a candidate is not the same as being a maximum or minimum. Some critical points are just flat spots in the middle of an otherwise rising function. So once we have a list of critical points, we need a procedure for sorting out which ones are the real extrema and which ones are just the flat spots. That procedure is called the first derivative test. The idea is straightforward. At a true peak, the function is rising on the way up and falling on the way down. So the derivative is positive just before the peak and negative just after. If you check the sign of the derivative on either side of the critical point, and you see plus then minus, then you have a local maximum. If you see minus then plus, then you have a local minimum. If the sign doesn't change, then the critical point is just a flat spot, not an extremum. So the framework for finding extrema is two steps. Step 1, take the derivative and set it to 0. That gives you what the critical point value is. Step 2, check the sign of the derivative on either side of the critical point, and that tells you what kind of point it is. Suppose, for example, that you run a small wholesale business and you're choosing the price for one of your products. Your daily profit depends on the price you set, and at a higher price, you make more on each unit sold, but you sell fewer units. The lower price has the opposite problem. So somewhere in between is the price that maximizes your daily profit, which is exactly what we would want to find. The numbers we're going to work with are these. At a price of P dollars per unit, daily demand ends up being 100 minus 2 times P units. Your cost to produce each unit is $10. So your daily profit is the price minus the cost, all times the number of units sold. Now that we have our profit function, the first step is to find the function's critical points. We take the derivative and we set it equal to 0. The profit function is a product of two pieces, so we use the product rule. Let's see how this maps back to the product rule definition. Our first piece, f of p, is p minus 10. Its derivative, f prime of p, is 1. Our second piece, g of p, is 100 minus 2p, and its derivative is negative 2. The product rule gives us f prime times g plus f times g prime, which ends up being 1 times the quantity 100 minus 2p plus the quantity p minus 10 times negative 2. Simplifying, we get 120 minus 4p. Setting that equal to 0, 120 minus 4p equals 0, so p ends up equaling 30. That's our critical point. The profit function has exactly one place where the slope is flat, and it's at a price of $30 per unit. Step 2 is the first derivative test. We check the sign of the derivative on either side of 30. At a price of 29, pi prime ends up being positive. At a price of 31, pi prime ends up being negative. The derivative goes from positive to negative as we cross p equals 30, so 30 is a local maximum. To find the actual profit at the optimum, we just plug 30 back into the profit function. The optimal daily profit ends up being $800 at a price of $30 per unit. What this is saying basically is that $30 is the price where the marginal revenue from raising the price one more dollar exactly cancels out the marginal loss in revenue from selling fewer units. At any price below 30, raising the price still makes you money on net. At a price above 30, lowering the price still makes you money on net. The critical point is where those two pressures balance. Victor puts down the letter. He's been considering a position in a specific stock for several weeks. The stock has a forecasted alpha that the fund's research team is comfortable with. It's small, but it's real, and an expected excess return on the order of a few percent. The catch is that the position has to be built up in the open market, which means his own buying pushes the price against him before he's finished accumulating it. He wants to know how much money he should invest in the stock before the cost of pushing up the price eats up more than the expected alpha is worth. So effectively, he's trying to figure out what trade size maximizes the fund's net expected gain. In our notation, that means he's looking for where dg over dn equals 0, where g is the net gain and n is the number of shares. Because g as a function of n is a polynomial, the power rule gives him the derivative directly. The fund's net expected gain on the position is alpha times n minus k times n squared. N is the number of shares he would purchase, and alpha is the per dollar expected excess return, which Victor's research has shown as 0.04. So at any size, the expected gross gain ends up being 0.04 times n. The minus kn squared term is the price impact cost. It grows with the square of the trade size because larger trades push the price further. Calibrated against the stock's recent volume and depth, k ends up being 0.0001. He differentiates, by the power rule, dg over dn equals alpha minus 2kn. Setting that equal to 0, n star equals alpha over 2k. Plugging in the numbers, the optimal number of shares to purchase is 200. He confirms with the first derivative test. At n equals 199, dg over dn is positive, and at n equals 201, it's negative. The derivative crosses from positive to negative at 200, so 200 is a local maximum. Victor takes a look at the number for a moment. He's been wondering what the rational quant has been doing with these trades themselves. He looks to see what their position size is, and he finds that they have exactly the 200 shares that he just calculated as the correct answer. It seems that they're coming to the same conclusion, only the rational quant has been figuring things out a little bit sooner. So that's the framework for finding extrema. Step 1, take the derivative and set it to 0 to get the critical points. Step 2, use the first derivative test to classify each critical point by checking the sign of the derivative on either side. Both pieces come straight from the basic property of derivatives, that the slope is 0 at a peak or a trough and changes sign when you cross one. The procedure works the same way for wholesaler pricing, position sizing, or anywhere else a function reaches a high or a low in finance.